Pretraining models entails three main stages. Stage 1. Pretraining trains the designed model, using the large-scale corpus, normally on some self-supervised tasks, to derive useful feature representation that contains general semantic patterns. Stage 2. Fine-tuning then tune the pre-trained model weights on the specific tasks using the training datasets from the downstream target domain, so that the learned representation can be tailored for the target tasks. In Stage 3 inference, the fine-tuned model can perform well with the unseen data on the target tasks, empowered by the synergy of general and domain-specific semantics learned from the previous two stages. VLPM is not a direct and simple combination of CV and NLP pre-training models. To present the review in a structured way, we generalized the VLPM into four major components. First, VRL raw input data, which defines the representative raw data streams from the single modality contents, being either vision or language. Second, VRL representation, which processes the raw data input into the desired format of modality representations. Third, V&L interaction model, which enforces the cross-modal modeling between the two modality representations. Fourth, V&L representation, which defines the possible cross-modal representations derived from the cross-modal modeling. We introduce the four components in section 2 and 3, and summarize the pre-training and downstream tasks in section 4 and 5. In the end, we also highlight some potential future research directions in section 6. For the VRAW input data, most VLPM adopts a single sentence as the raw language input, which aligns with a single image as the raw visual input. The first example here shows a pairwise text-image data that are semantically aligned, which is commonly used for VLPM pre-training. Some specialized VLPM apply multiple sentences as raw language input for tasks such as visual dialogue and multimodal translation. The second example demonstrates the input data format for the visual dialogue task, in which multiple pairs of questions and answers are involved for understanding the corresponding image. Similarly, there also apply multiple images with multiple sentences as raw input. The third example illustrates the vision language navigation data, which contains a set of images along the navigation trajectory together with the corresponding instructions. To encode the raw language and visual input data into modality representation for cross-modal modeling. Most VLPM directly adopt the BERT formatted sequential input representation format, with minor modification for both language and vision, due to their application of transformer-based architecture. First, let's see how the language input encoding can be conducted. We identified two types of early fusion strategies for the language encoding. The first one is the vision-to-language early fusion at raw input level. For example, in the ROI-based OSCA, they further utilize the object class tags, detected from image as part of textual input, and encode the tags together with the language tokens. Another type is vision-to-language early fusion at representation level. For instance, the VBERT extends the visual feature to the language side as the fourth type of embedding, which uses the visual feature of the whole image to represent each language tokens. These early fusion strategies intend to ease the cross-modal alignment modeling by reducing the semantic gap beforehand at early stage and worth further exploration. Now, let's have a look at the vision input encoding. Unlike the language, that naturally entails the textual tokens as words, visual images requires extra designs for defining the visual tokens. We refer it as the visual representation granularities, which defines how image pixels are split into groups as visual tokens. It is an important decision of design, since it decides the alignment level of cross-modal modeling in the image content, i.e., the source of cross-modal interaction. In this table, we summarize four main types of visual representation granularity. The ROI-based VLPM that uses object regions as visual tokens. ROI stands for region of interest. It assumes that most image-text pairwise data is supposed to have its text described the salient object regions in the corresponding image. They normally apply a separate pre-trained faster RCNN-based object detector to detect the object regions and extract their visual features for representing the visual tokens. Before feeding the BERT formatted language and visual representation into the cross-modal interaction model, some VLPMs further conduct additional intramodality processing to the language or visual representation or both to reinforce the representation of the modality. With the prepared language and visual representation, let's go through vision and language interaction modeling. There are two types of mainstream VLPM model structures. The first type is single-stream VLPM, which directly fuse the BERT formatted language visual representation by using the joint cross-modal encoder at the initial stage. The second type is double-stream VLPM, that separately apply the intramodality processing to two modalities along with a shared cross-modal encoder. Note that the way of classification is mainly based on the perspective of data stream and intramodality data handling before the cross-modal modeling. So, we propose three main categories on the vision-language interaction modeling. First, the self-attention-based VM directly apply single-stream self-attention module to the modality representations for cross-modal modeling. Most single-stream VLPMs, and some of the double-stream VLPMs, are considered as this type, since they directly apply single-stream self-attention module to the modality representations for cross-modal modeling. They simply concatenate the language and visual representation to produce an integrated sequence representation. Second, the co-attention-based VLIM decouple the intra- and cross-modal modeling processes, which keep two separate streams of transformer blocks for each modality that are entangled only at the specific cross-attention sublayer. These sublayers enforce exchange of the key and value in self-attention module between the two modality streams. In this way, they limit the cross-modal modeling only to those co-attention sublayers, while leaving the rest of the sublayers independent to focus on intramodality processing and modeling. The third type is VSE-based VLIM, which simply utilize the dual encoder structured model with visual semantic embedding VSE-based cross-modal contrastive learning. It is mostly applied for retrieval task-focused VLPMs. They tend to have a special focus on large-scale cross-modal retrieval, with high demand for efficiency. They utilize the intramodality processing to derive the vision and language representation, which the similarity-based cross-modal alignment would be modeled in the shared VSE space at the global level. This dual encoder structure eradicates the fusion-style attention-based VLIMs that are computation costly and time-consuming. With the well-defined input format and model structure, the pre-training can then be conducted. The mostly used is the large-scale Webley collected dataset, with enormous size and diversified nature. For example, the conceptual captions, CC, with roughly 3 millions of data pairs, and SBU captions with around 1 millions. It is found that a larger sized corpus leads to better performance in downstream transfer tasks. Secondly, the combination of out-of-domain and in-domain datasets are also common to provide both general and target domain patterns. The most popular combination is having conceptual captions or SBU captions as out-of-domain while COCO or visual genome as in-domain datasets. The in-domain dataset can also be task-specific datasets that specifically come from the commonly evaluated downstream tasks. The inclusion of in-domain dataset for pre-training is shown to lead to better domain adaptation in downstream inference. Furthermore, some VLPM with focus on tasks, such as visual dialogue, also apply domain or task-specific data only for pre-training, due to the reduced suitability to the above text-image datasets regarding domain nature or data format. Let's go through three most commonly used cross-modal pre-training tasks. First, the cross-modal masked language modeling, CMLM, extends the masked language modeling, from BERT pre-training to the multimodal setting, for learning the contextualized vision language representation, utilizing the attention-based VLIM. Second, the cross-modal masked region modeling, CMRM, is the vision-supervised counterpart of CMLM, which is initially proposed by ROI-based VLPMs. Third, the cross-modal alignment, CA, is commonly applied by VLPMs with attention-based VLIM as a binary classification, to predict whether the input image-text pair is semantically matched or not, based on the global vision and language representation. We also provide the summary of the 8 commonly used vision language understanding tasks, VQA and VD, SIMR and VRD, NLVR and VCR, REC and VLN, and IC, MMT for 2 last via generation tasks. In conclusion, we present an overview of the recent advances in vision language pre-trained models. We propose promising future directions for the VLPM. First, most VLPM focus on masking, at the task level or input level, but other cross-modal alignment strategies are encouraged. Second, it is worth exploring, step by step, how the multitasking can be implemented for VLPM pre-training, that can generate the best transfer performance on the specific targeted domains and tasks. Finally, so far, the trained VLPMs can be only evaluated during the downstream tasks. It is worth exploring some metrics, such as perplexity, during the training procedure.